started. Thanks for being here for this afternoon's research seminar. My name is Cinnamon Moffett, and I'm the research program manager here at Oregon State University's Hatfield Marine Science Center. This is a hybrid event, so we have folks in the room and we have folks online, so welcome everybody. We are very excited to have you here. Just a couple little logistics for those folks that are online. We will be answering questions at the end of today's event, so please put in your questions at any time into the chat and we will work through those at the end, or at the end of the presentation you can raise your virtual hand and Sana, who is here with us, will help monitor those questions and make sure you can be unmuted and ask your question verbally. For those folks that are here in the room, you will need a mic to ask a question at the end of the presentation. You are welcome to either go to the mic stand or raise your hand and I'll run around and I'll bring you this microphone. But please make sure you have a mic to ask a question so those folks that are online can hear those questions as well. Other thing I wanted to do was make a quick announcement for next week's seminar. We have a powerhouse coming. You might have seen their pictures hanging up all over the place, but the Cozy group is going to come and talk to us about microplastics in the prey of gray whale diets. So that will be a really interesting talk, and it will be a hybrid event. So again, you can be in the room or you can be online. But for today, our speaker was invited by our own Drummond Biles, the manager of our iLab. So I'm going to have Drummond come up here and introduce today's speaker. And he has the bio on paper, so I'm a little nervous.
That seemed to be the right way to do it. Yeah, so I'm really pleased to introduce Matt Johnston. We were able to entice him out here to come learn a little bit more about what he's working on. And it's part of a larger project that we're working on to bring some CLV faculty out here, as well as start to run some classes out of the innovation lab. So maybe for the end, we can kind of talk about that and where we're going a little bit. But yes, I have a paper to describe all of the excellent things. And I think because, Matt's kind of bringing in this new space, I really wanted to give a sense of the area of his expertise, especially because it relates directly to a lot of the things we're doing here. So Matt Johnston joined Oregon State University in 2014, where he's currently an associate professor in the School of Electrical Engineering and Computer Science. He received his BS degree in electrical engineering from California Institute of Technology and the MS and PhD degrees in electrical engineering from Columbia. Prior to Oregon State, he was co-founder and manager of research at Hilexis, a Caltech-based spin-out developing instrumentation for real-time PCR. It's a famous word. From 2007 to its acquisition by Illumina in 2010. He also worked as an associate at the life sciences venture capital firm, Ascent Biomedical Ventures in New York City. His current research includes integration of sensors and transducers with silicon CMOS integrated circuits, stretchable circuits, which I'm totally curious to hear how that works, and sensor systems, lab on CMOS platforms, bioengineer, energy harvesting, and low power distributed sensing. So thank you for giving me a wonderful script to read. Didn't say that he has the ability to walk on water, but we'll get to that later and tell us more about that.
Thanks,
so, without further ado, Matt.
Great, thank you. All right, thank you all for those of you who are able to make it in person. Thank you to those out in the ether. Hopefully you can hear me okay and maybe see me. I can't see me, which is better. So I'm going to be talking about a few different areas we work in. The core theme here is sensors. So you'll notice a couple things. One, none of these are in the ocean, but we'd like to change that. Two, as soon as we see data, we're done. Right? We build sensors, we create data for other people. And so we're constantly looking for new applications and new places that sensors need to go and people who can do something useful with data that we're able to help create. So broadly, my lab works on bringing low power, small form factor electronics, largely based around integrated circuits, into new sensing applications. So historically, this has been biological applications and chemical applications, as well as physical sensing for temperature, radiation, ambient light, things like that. So anything in sort of the world around us that we might want to sense, we're interested in, and we've worked in a lot of those areas. My background is really in bioinstrumentation, but that has since merged into looking outward at all the many things where we need to go and quantify something out in the real world. So the core of a lot of these will be integrated circuit sensor platforms. I will try to steer clear of circuit details since this is not largely a circuits audience, but some of that is unavoidable. We do microfabrication for building MEMS and NEMS devices for other kinds of sensors and transducers. We move sort of outward to chemical and biological applications. And then we are also often sort of wrapping these up in handheld or deployable sensor packages to show sort of what can be achieved through this miniaturization. So often this takes the guise of there's some benchtop instrument that works in the lab, and we want to use more modern technologies such as ICs, microfabrication, and heterogeneous integration, which is bringing together different manufacturing technologies to shrink that down and either maintain performance or increase performance, but also increasing density and parallelization and really just scaling. So that's sort of a common theme of where we start looking for different projects. Brief introduction, since these are the people on the left that really do all of the research, as you're well aware. So I want to give a shout out early and often to my graduate students who do and have done all the work you'll see here today, as well as my colleagues. There's a lot of people at Oregon State working in circuits and integrated systems. And those pictures, well, you're all aware of what Oregon State is, since we're here in part of it now. All right, so today I'm going to talk about stretchable and flexible circuits. I'm going to talk about some of the work we've done on sensors for wind turbines to show sort of how we get out and do some field work, and some of our work moving towards electronics without batteries, in this case for medical applications, that we believe there's sort of related applications anywhere you don't want to have to be constantly recharging your sensors. So how are all these things related? Well, let's start my stopwatch so I don't lose track of time. One of them is low power and low cost electronic sensors. So, you know, smartwatches, cell phones, we're surrounded now by sensors and everything from cameras to microphones and light sensors that we're very used to, and you can fit a lot of them in a small package and you can have advanced signal processing, but that's all still pretty new in the scale of things. And so we're trying to take the same technologies that have enabled those advances and apply them to scientific sensing applications. Additionally, low power means we increasingly need to have some amount of signal processing and intelligence upfront right at the sensor. So in a sensor system, a lot of your power is just spent in wireless transmission, if it's wireless. And so you really need to minimize what you're sending and make sure that you're only sending sort of important data. Sort of improvements in energy harvesting, which we'll talk about, but gathering energy from the ambient environment, either solar or thermoelectrics or RF, hopefully can eliminate the need for battery recharging and drive towards power autonomy. And then a lot of these applications require sort of new packaging techniques, which is where we started looking at stretchable and flexible electronics. So though these seem like kind of disparate things from our perspective, these all sort of share these core fundamentals that we've been exploring. All right. One slide primer to integrated circuits, because I use that term a lot and it's not something everybody's familiar with. Although in Oregon, with places like Intel, it should be something that we become familiar with just to stay aware. So you've probably all seen a printed circuit board. These are the green fiberglass boards that are inside all modern consumer electronics. One of the things that is soldered to it is an integrated circuit. So that's where the thousands or millions or billions of transistors lie to do digital computation, analog signal processing, amplification, so on and so forth. So that is an integrated circuit. Those are designed in CAD, just using sort of drawing software, similar to use for mechanical drawings, but here you're drawing transistors. Those are fabricated at a commercial CMOS foundry. So this is not the sort of thing that you can build at a lab, in a university clean room lab. This is an advanced manufacturing technology, and so we can do the design at the university, but then it's still fabricated at a commercial foundry. Now, when that wafer comes back, that wafer has many, many, many copies of the same set of circuits, so it gets cut up into little pieces. Those get packaged out, and that's what goes onto the printed circuit board. Okay. So integrated circuit design My grad students spend most of their time on that top portion, at least the ones who work in IC design, really in doing the circuit design in CAD. And then at the very bottom, when we get them back and we do the electronic testing. One thing that we also do that I won't talk much about today is we can steal the chips at this part of the process before they're packaged, where they are bare bits of silicon with integrated circuits and active electronics on it. We could take that and do other kinds of packaging or build other MEMS devices on top of that. So we have sort of a lot of work in integrating microfluidics with integrated circuit sensors for biosensing and point of care applications. All right, so after all that preamble, let's look at one of these areas. So this is our work in stretchable electronics. This work has been led by Callan Votsky, who's a current PhD candidate, and Kyle Clocker, who actually graduated recently. And we have many undergraduate researchers working in the lab as well. So we just looked at a printed circuit board. So this is a rigid fiberglass-based printed circuit board. You can also make them very thin on polyamide or other sort of flexible polymer materials and get flex PCBs. But that's as far as you can get, right? So you can have rigid or you can have flexible, but flexible is not stretchable. So stretchable circuits, similar idea, where you have components connected by wires, but now both the substrate that they're built on or in and the wires themselves can stretch. The components are still rigid. So here, sort of hard to see. We're working on better videos, but there's a blinking LED. This is one of our very first earliest stretchable circuits where we just have a timer blinking an LED, but all of it can be stretched. So the idea is, at a starting point, is to build stretchable printed circuit boards. Why? Well, we see a lot of emerging applications that might benefit from this or might require this. So a lot of this work actually came out of our collaborations with soft roboticists. So soft robots are things like robotic octopi or other things where the whole thing may need to be squishy or compressible or conformable. And in that case, you can't have big rigid components embedded in that. There are also interesting applications in wearable devices, electronic skins, and things like that. So we work on sort of the core, how would you build it aspects of this, but we're starting to move into looking at some of these more from an application perspective. So previously, if you wanted to stretch circuits or build stretchable circuits, you had a couple of options. So one is you still have rigid wires. These are thin gold wires, but you build them in these serpentine traces, and you put it on a stretchable substrate. So now when you bend it, these wires can expand a little bit. Okay, if you bend it too far, they break and they stay broken. But it works well enough, and you have high conductivity because you can still do this in gold or copper. There's a lot of work in conductive inks. So these are metallic particles in some sort of polymer or carrier material that now allows you to stretch them. One downside is that the conductivity is much lower, so you have a lot more loss than you would with copper or gold. Another problem actually is that you no longer have sort of a solid metal. You've actually got all these little metal particles. And so conduction happens sort of from particle to particle to particle in what's called a percolation network. And so now as you stretch these apart, that really falls off. And so the conductivity gets a lot worse and it's very nonlinear. So what we make use of are liquid metal materials. So mercury and gallium are both liquid at room temperature. We avoid mercury for probably obvious reasons. We do work a lot with gallium and alloys of gallium that are liquid at room temperature and non-toxic, and are a true metal. So if you confine it in sort of a tube that's stretchable, it's still just a solid metal conductor. It's not as conductive as copper or silver. In fact, it's about 10 times worse, but it's still as good as you can get for sort of truly stretchable conductors, at least so far. So we do one other thing, which is to turn it into a paste. So gallium on its own is sort of watery, and it's hard to build structures with. If you add nickel and ultrasonicate it, you can turn it into a metal material that has a consistency sort of like toothpaste, which makes it a lot easier to use for things like 3D printing or stencil printing. And so this is where this work sort of starts, but it is still fundamentally a liquid. So you still get solid conduction through that. So the first thing we did was start modifying 3D printers to print now with this liquid metal material. So what you're looking at is a 3D printer that has been modified to take this liquid metal material. There's a syringe full of it, and then air pressure pushes it into the extruder. And then there's an auger that forces that out of the tip at the bottom. It's printing on a silicone bed. So silicone is a rubber material. And there's different formulations, but they're all basically silly putty. So it starts as a liquid, 2-part liquid, you mix it, you pour it, you cure it, and now you've got a very stretchy base on which you can print these electronics. Then you can pour more silicone on top of that and cure that, and now it's fully embedded, right? So if you've got a liquid metal line and you cure silicone around it, you sort of form this tube that is exactly the shape of the liquid metal and confines it. So the design is just like regular printed circuit boards. This is some of the earlier work where you can see lots of bubbles and blurbs, and it was not a perfect process. It's gotten quite a bit better. But at the moment, or sort of in this work, we're really just doing simple printed circuit boards, right? As simple as you could get, things you could build in a lab anyway, but now they're fully stretchable. So one thing, and this is a good time to point it out, is that we focus on is using standard components. So there's a whole separate universe of research around flexible transistors and organic semiconductors and sort of large area electronics where all of it is flexible. We, in contrast, are really just building stretchable wires. So we still take advantage of silicon-based electronics and all the power efficiency and scale that comes with that. But they're small relative to the wires, and so the whole thing is still stretchable. You can also stencil this, and it's a little hard to sort of see what we're looking at, but we're actually looking at a steel stencil with cutouts in it. This is very common for soldering, for solder stencils. But you just sort of put the paste on top, smear it across, lift the stencil away, and then you can just place your components. Okay? And this allows us actually quite a bit cleaner lines than the 3D printing. So now with that, we can build a variety of stretchable circuit architectures. We can also build sensors into them. So that is a printed strain sensor, and then readout for that strain sensor, and then that changes the color of an LED based on what it measures from that strain sensor. Okay. Now, from electrical perspective, we want perfect wires. Perfect wires have no resistance. These wires do have resistance. And as you stretch it, that resistance changes. So that's not great from an electronics design perspective, but it's something we can take advantage of and using that as a sensor. So in fact, the resistance goes up with the square of the stretch. So if you stretch it to twice its length, you have 4 times the resistance. And so that's good actually for building strain sensors, okay, which measure sort of lateral displacement. So one of the ideas here is that if you're building a stretchable circuit, all of the wires connecting all of your components are going to change resistance. And so in some cases, you need to sort of fight against that or compensate for it. But in other cases, you can use that as a sensor that you get for free. So if there's different components at each sort of location Z, and if we stretch the grid in this direction, those resistances go up. And if we have a way to measure that, we can now sort of tell that our circuit has been stretched. Okay. So this is an area we've been looking at where, regardless of the stretchable circuits you may want to build, they may have the ability to sort of sense their own deformation or to estimate their current conformation. So as an example of this is the device we built on the right. So this is a 3x3 grid. At each node of this grid is a little microcontroller, okay, that can measure the voltage at that node. This is actually a 5-layer circuit. It's sort of hard to tell because it's just sort of stacked grids. But what this really means is that we've got active devices at each node. We can talk to all of them just from the corner here over this 4-wire interface. So we have power and data from just one location. And we can ask any of these nodes, what is the voltage at your node, right? And as this gets more stretched, the resistance goes up, those voltages change, and we can use that to measure that deformation. So right now, this is just sort of a test object. Can the grid tell you that it has been deformed? But you can imagine integrating this into other soft robots, other wearable devices now, where you are measuring that change in conformation. So in this example, we've now stretched this grid in one direction, and the resistance changes sort of as we would expect. So because we're only stretching in Y, the 1,1 to 1,3 has little change, okay? In fact, those nodes actually get slightly closer together because as you stretch it, it gets narrower. 1,1 to 3,1 has the most change because that's the longest change in sort of path length, whereas the middle node is somewhere in between. So we can simulate it, we can measure it, and the data matches pretty well. And so now where we are is sort of solving the other part of the math problem, which is if you have all these measurements, can you go back and solve what is the shape? Okay, so it's a grid for now. We're looking at other arrangements and other formations of this. Okay. The other thing, though, is that now that you have sort of the ability to place electronic components throughout these silicone objects, you could also be putting in other sensors, other actuators, optical communication, wireless communication. It's just a printed circuit board, right? But now it's stretchable. So we're excited to see where this can be pushed and what other things we can integrate into these technologies. One sort of cute demo, I think, is building sort of other wearable sensor devices. So, you know, glove sensors that now I move my hand and that is measured by the stretchable sensors, and that can be used to control simple robotic hands and things like that. So I think this is actually an area where we'll see stretchable consumer devices sooner rather than later around sort of controllers for computer interfaces that are based on action. And you can embed feedback also for haptics. So these are some of the areas that's headed. Okay. Any questions about stretchable electronics before I entirely change topics? Yes.
I guess my question is fairly simple. Will you see change in that conductivity over time?
Great question. So not shown here are a couple of experiments we've run. One is we take these sort of test strain sensors and we stretch them over and over again. So we built a device that just stretches them day in and day out. And we've tested up to at least 100,000 sort of stretch relax cycles and seen no change in conductivity, which actually really surprised us because gallium does oxidize. We expected that to degrade and the silicones are oxygen permeable. So we fully expected degradation, but haven't seen it at sort of at least 100,000 cycles. We have not done that at elevated temperature, but at least at room temperature, it seems to hold pretty well.
Any questions online? Okay.
Great. Okay, other sensors. So sensors for wind turbines. So this work was primarily done by PhD student Kyle Clocker over a period of about 4 years through a couple of different projects with the Department of Energy, as well as Calder Wilson, who was an undergraduate and is now a master's student at Oregon State, worked on this as well. So wind energy is growing, as we're aware, and as we need it to. It will become an increasingly significant portion of energy production, both in the US and worldwide. And additionally, sort of we think maybe in this country, especially of onshore wind turbines, but offshore wind turbines, you know, just off the coast in the ocean are going to become an even more important player here because you can build bigger wind turbines and bigger wind turbines are more efficient. The problem is that wind turbines have some negative effects on wildlife. So birds and bats especially are hit and killed by wind turbines, either because the wind turbines are built in their flight path or because they fly too close. So this is a big problem. And from a regulatory perspective, it's especially problematic for protected species. So golden and bald eagles, as well as a number of protected bat species and protected coastal species. So wind energy operators need to both monitor and estimate every protected bird take that happens. And that's a hard problem. So onshore, they do carcass surveys. So they have people that go out and they look for carcasses. And from that, they sort of estimate overall wildlife impact. That's already challenging because of scavengers and other things like that, and the human power involved in these carcass surveys. And offshore, it's just not an option, right? There's no carcass surveys that can be done. So this is sort of the origin of these set of projects around building sensor systems that can detect collisions, blade strikes, and then basically take a picture of whatever hit it. Okay, so you know that the blade hit something or something hit the blade, and you get a picture of it. So it's a simple concept, but challenging to implement for a variety of reasons. So one of the systems we built for this is a set of sensor modules that sit at the root of the wind turbine blade. And they've got vibration sensors and accelerometers, and they're constantly monitoring and looking for collisions with the blade. Okay, but it's one sensor, and the blade is on a small wind turbine, about the width of this room, and on a big wind turbine, much bigger. And so it's challenging, just sort of the noise and the signal levels. But this is a good starting point. The other thing this has is a camera, and the camera is pointed down towards the tip of the blade, and it's constantly looping a video. Okay, and now if a collision is detected, it saves the last video, right? So we can't go back in time and take the video, obviously, but as long as you're constantly looping a video and then you can decide when to save it, now you can get a picture, hopefully, of whatever impacts the blade. Oop. Okay. There's also other things integrated in here. This is all off-the-shelf components with sort of custom fixturing. So this is not custom IC design. But this is an example of when we take commercial sensors and integrate them together in other modules. So you can see this here mounted now on the root of a wind turbine blade. I guess that'll be on the next slide. We do a lot of this testing in collaboration with the National Renewable Energy Lab, Flatirons campus, just outside of Boulder. Okay, so in an early field test, one of these modules mounted on each of the blades. You can see it in the orange boxes there, although you'll probably have to just believe me that that's what I've drawn the box around, because it's probably hard to see. And then the other thing you need are blade strikes. So fortunately, birds and bats don't hit blades that often. But that presents a challenge for field testing when what you're trying to measure is collisions. Okay, so instead, we fire projectiles at the wind turbine blades at a federal facility. So basically, it's tennis balls and potatoes. We've moved to more advanced projectiles that I'll talk about. Tennis balls are good because they're easy to work with. It's easy to buy lots of them, but you have to pick them all up. Okay. And potatoes, we thought would be better because they degrade. And in reality, you still sort of have to pick them up because otherwise they just attract wildlife. So there's an air cannon here. The wind turbine's tall, so you can hit it from the ground with the air cannon. Your accuracy goes way up if you put the air cannon in a personnel lift with personnel and then fire from closer near the blade. So this is how this testing is done. It's phenomenal. And the folks that help us with this at NREL are just amazing. So we've run 4 or 5 different field tests, and it's gotten more efficient, but they all follow sort of the same basic setup here. Okay. But as most of you are aware, there's a challenge inherent in this field testing is that, we do a year's worth of development and we get a week or 2 out in the field. And if the weather's good, we get a few good days of data, and that's it, right? That's just sort of the reality. So there's always a challenge in how much data you can get. Okay, so don't stare at this one too long, but this is the view from one of those video cameras as it spins around and around and around. And then this is at regular speed, and then on the right here it's sort of the slow-mo, and you will see a tennis ball come in and bounce off. Okay. And that picture was automatically captured after it sort of detected that tennis ball striking the blade and then went back and saved off that video loop. Okay. So you can imagine inputting all sorts of machine learning to do image recognition and things like that. There's sort of a separate part of these projects that looked at that. But in reality, for wind turbines specifically, the idea at least is to get a picture, send it to a wildlife biologist who can say that was a tennis ball, or what species it might have been. Additionally, we get a lot of data. So each one of these modules, so there's 3 modules, one on each blade. Each one has a contact microphone. and the camera, as well as accelerometers and other sensors in them. So we do get a lot of sort of raw data out of these systems. Every time you see a sinusoidal wave, that's because the wind turbine is spinning. And so the accelerometers and the gyrometers mostly pick that up, right? And then if there's a collision on top of that, you can hopefully see that. Okay, so the contact microphones are cheap and easy. These are 50-cent piezoelectric buzzers, basically, that you turn around and use as a sensor. All of the electronics are sort of hobbyist grade. So this is a relatively inexpensive system. Installation is by far the most expensive part of this sort of system. And when you do get a collision, if you're lucky, it's quite clear, right? We can all see that that's a collision, and none of us would have a hard time saying something happened there. But there are challenges because not all of them look quite that obvious. So this is now an accelerometer data, and there is a little collision there. I happen to know this is a collision. You could probably have picked it out anyway, but whether it was collision or a noise event can be challenging, right? And so there's an inherent challenge in, even if we can see it, can we get a computer to see it, right? I can easily tell you if that's a dog or a cat, but it took many decades of research to get a computer to do that. Now it's easy for a computer. But just because we can see it doesn't mean it's easy for the computer to determine that. Okay. We also have we have an accelerometer, a gyrometer, and a contact microphone. The accelerometer and the contact microphone are probably the most useful. A gyrometer does pitch, yaw, roll, and that is less good for detecting impacts, but really useful for detecting other motion artifacts. So right at the end of this recording, the blade pitched. So the blades are constantly pitching to track the wind and to sort of maintain their preferred rotational speed. And you can see that in some of these sensors. But those artifacts also present additional challenges in determining some of these collisions. So these are example collisions across those sensors, very similar data, but just sort of explaining why it's not simple, even if we can see them, to detect the collision. So some of these are turbine motion artifacts. Other ones are, you've got this big sine wave on which everything is superimposed that you have to deal with. Okay. So the simple way to do this is take your data and sort of look frame by frame and see, is there a big excursion? Is there somewhere where the maximum and the minimum is larger than some threshold, right? This is sort of the simplest way to imagine algorithmically doing collision detection. Okay, but the problem, as we said, is there's a bunch of other things that sort of look like collisions, and not all the collisions are large signal. So I won't go into a lot of depth here, but this is probably a good data set for machine learning with some challenges and some caveats. So the idea here is that we can't just set a threshold, but if we have lots of recorded data, can we learn from that data and be able to tell what is a motion artifact, what is an actual collision? Because we know the data that has collisions because we took timestamps of when they happen and things like that. One of the challenges is that there's not a lot of data, right? As we discussed, you don't get that much field time. And so most of these machine learning algorithms require a lot of input data, and we don't really have it. The second one is that the data sets are highly imbalanced. What we mean there is that if you sit and record, we get lots and lots of recordings of the wind turbine just spinning and nothing happening. And we get a few collisions, right? Or maybe over a few days, we get a few hundred collisions in a really good week, but it's imbalanced. So we have lots and lots of sort of baseline data and not much collision data. And that actually is a challenge for most algorithms as well, when you have that imbalance. So we need a classifier that can deal with that. And so we investigated a lot of different ones. And this is sort of the approach we took, that we won't go into it, but one thing that I will mention here, and it made intuitive sense to me, is you start by doing anomaly detection. So if you have a bunch of sort of baseline data, you can learn what that data looks like. And then you can say, oh, this other one doesn't look like that. Okay, so anomaly detection is very good for imbalanced data sets because you start by sort of learning what is normal, And then from that, you can sort of determine if something is an exception to normal. So that's an important sort of feature of this approach here. So to just sort of step through how this algorithm works, you start with your raw data. You run this through a high-pass filter, okay? And primarily what that's doing is just removing this spinning of the wind turbine blade, because that's a relatively low frequency. Then what you do is you walk through this and you take sort of frame by frame. These are overlapping frames. And in each frame, you look at a bunch of different features like the variance and the max min. And sorry, these are auto advancing. Not playing nicely. Okay. And from that, you do your classification. But the anomaly detection first looks at what is normal, pulls out the frames that things that are not normal, and then you use those abnormal frames to do all of your training and testing. And so we know which of those frames are a collision and not a collision, but it's already just a subset of the frames that were abnormal. So this process ends up being a lot more efficient than the other approaches we investigated. Okay, so this is an example of this frame, or of this frame from this recording, where the things in the dotted boxes, the algorithm determined these were abnormal frames. And then within those, where was there actually a collision? And this is correctly labeled, correctly identified. Okay. So due to time, I won't go to the details here, but basically you can look at this as either sort of true positive, false positive, or precision and recall. Naive is this just sort of idea of having a threshold, as well as having a classifier, and having a classifier with the anomaly detection built in, and performance gets better and better. Okay. Now this matters because if you imagine this system and it has too many false detections, then a wildlife biologist has to look through 10,000 images, right? Which may be overwhelming, and so you haven't really helped the problem. Whereas if you sort of back off on that, you start to miss events. So there's always this trade-off in classification between sort of true positive and false positive, and true negative and false negative. Okay, so it's never going to be perfect, but you can start to improve that. All right. One other thing you can, so the next part of this project that I'll go through a little bit quickly is increasing that sensitivity. So as I mentioned, you have one sensor and a really long blade, and that's probably not sufficient. If the blade strikes something out near the tip, you're just not going to see it by the time that vibration sort of moves back through the blade. So the idea here is, okay, let's put sensors further down the blade. Let's make them wireless. Let's make them power autonomous, so that you're never going to be able to go out and recharge those, and you don't want to run wires down the blades. So just make some patches that you can stick on, power themselves, and talk back to the module at the root. So this is sort of a semi-custom design. So this is custom electronics using commercial parts, and this is our blade patch module. There's not sizing here, but it's about the size of a cell phone. So it uses solar power and a small battery to constantly recharge, and it's designed to be very low power, and it only transmits if it detects something, is the idea. So if a collision is detected, it can wake up, burn some of that power to tell the root module, hey, I think I may have detected something, save that last video, right? So it's a simple idea, but by building these sort of small form factor and power autonomous, it's easy to then go and stick them down the blade. This is just an example of how we validate this sort of thing before we go up to the tall wind turbine, which is we use wind turbine blades on the ground, right? So for obvious reasons, this is a lot less labor intensive and easier to access. So this is a blade that's been sort of taped off at measured intervals, and now we can have collisions at varying distances from these sensors to get an idea of what the sensitivity looks like. It's not perfect, right? Because this blade is not spinning, it's not attached to a hub, and so there's still a reason to do real field testing, but this is a good baseline that lets us assess sensitivity before we go out to the real wind turbine. The chart on the table on the right is measuring basically if you have your root module and then you have sort of a patch closer to that and a patch farther from that, okay? And now your collisions, your fake collisions happen at various distances out, okay? When you're close to the root module, you can detect it and the near patch can see it. As you get out towards the end, the far patch can see it, even though the root module can no longer see it, and the near patch can maybe see it. And this just sort of validates that, yes, if a collision is out near the tip of the blade and you have a sensor out near the tip of the blade, you have a much better chance of detecting it. So these are all on a wireless network. This was originally Bluetooth, and then we moved to LoRaWAN, which is just a long-range sensor wireless protocol. So there's a lot of networking involved in getting this all to work. But in the end, the sensors you just sort of stick on the blade. Okay, so back out to NREL, and same basic setup at the root module, although we've added a second contact sensor, but now you can see the 3 sensor blades distributed along that are now communicating back wirelessly to this central module. I say it's easy to install these, but in reality, it took 2 days and a ropes team to manage to epoxy these to the wind turbine blade. But as I said originally, just for the root module, installation is by far the most expensive part of these systems. But when we think about these things, we're trying to demonstrate what might be possible and what might be worth future commercialization, future integration, right? There's no reason these have to be outside the blade. In fact, you wouldn't want them to be probably aerodynamically. So they could be part of the blade manufacturing process, things like that. So, okay. And then this is all the networking hardware that sits on top to talk to them. Okay. The only difference here is NREL actually developed a new air cannon that is linked to the rotational position of the blade. So they can, once you figure out how long it's going to take to fly, you can almost hit it every time, or you can at least be at the right place at the right time for the blade spin. We're not the only people doing projectile testing out there anymore, so they thought it was useful to develop that. That's been really useful. And then additionally, we moved to these projectiles that are sort of balsa fins with a gelatin plug on them. So they're biodegradable, and mechanically they look more like a bird than a tennis ball does. Okay. So that was actually a really recent field test. We came back with a pile of data that we're now sorting through. If you put it back, if you take the patch data and run it through the classifiers we'd used previously, it's almost perfect, which really just means we don't have enough data, because of course it's never going to be perfect. So it's a good starting point, and it's promising, but it really just means if you really want to test these, you need a lot more data. Another thing we think about is other ways to sort of detect these impacts other than just looking at sort of the amplitude domain. So the top 2 plots here are effectively just the voltage coming out of a contact microphone or accelerometer. The bottom 2 plots are spectral plots, where we've got time on the x-axis and frequency on the y-axis. And what we can see here is on the left, we know there's one impact, and I've boxed that. And you could sort of see it in the voltage domain, but it's a little easier to see in the frequency domain. And on the right plot, we know there are 3 successive impacts here because we made them. Can't see it all in the voltage domain, but it's visibly there in the frequency domain. And so I think there's still a lot more here on the detection algorithm side to automate this process. Okay. All right, I think I'll go ahead and just talk a little bit about our last topic here, just to make sure there's time for questions at the end. But I'm happy to answer questions about the wind turbine work as well. Okay, finally, battery-less sensor systems. So we're very interested in power autonomy, because as we have millions and billions and trillions of sensors going out into the world, we can't go around charging all of them all the time. It doesn't necessarily have to be batteryless. It just has to be power autonomous. So in this case, we're interested in sort of truly batteryless. And this work was primarily done by a couple of my previous PhD students. So the motivation here originally was for wearable devices, either consumer or medical. There's a lot of things that people want to measure. And right now, all of them require batteries. But there's a lot of sources of energy for a human out in the world. Solar is good and abundant during the day. Body heat is abundant at all times, although harder to extract energy from. And there's also biomechanical energy and other places to get this energy from. So we took an interest in thermoelectric energy harvesting. So this uses what's called a Peltier device, or a thermoelectric generator, which is this cool physical property of some semiconductors where if you put a temperature gradient across it, you get a voltage. or if you run a current through it, you get a temperature gradient. So these are also used for solid state heating and cooling in servers and other things like that. So it's a solid state heat pump. So if you put this on the human skin, which is warmer than ambient, you can get some energy out of it. Now there's two challenges. One, it's not a ton of energy. It's microwatts, which is enough to power sort of simple sensor devices. But the other challenge is very much on the electronic side, which is that though you have a usable amount of power, it's coming out at a very, very, very small voltage. And modern electronics, even the most advanced electronics, still require almost a volt to operate. Okay, and so you need to get from a very, very small voltage to a much, much larger voltage, and you need to do it efficiently. Okay, so sort of fast forward. Well, so there's two challenges here. One is getting it all to start. If you imagine starting a car, or an internal combustion engine, right? You need a certain amount of energy to get it started, but then it can idle at a really low trickle. So it actually is true for these sort of DC-DC converters that go from small voltage to large voltage. Once they're going, they can keep going at a pretty low voltage input, but you need something to get them started. So most of these systems still have a battery just to get started, and then they can operate. So that was one of the challenges we looked at. Efficiency was the other one. And there are, 5 years and 50 slides I'm not going to show in between sort of that idea and getting a working device. But in the end, what you get is this really cool little microchip circuit that you attach a thermoelectric generator. It's just a little ceramic device that you can buy online, and you put your hand on it. It's the only thing connected other than test leads to that chip, and the voltage pops up, and you get a usable voltage out of it. So this is sort of a first demonstration that, yes, human body heat is enough, both to start this up and to get a usable voltage out of it. Okay, so the input voltage here can be as low as about 60 millivolts, which is low enough to start with human body heat. Coming out of this is 1.2 volts or 1.5 volts, which I assure you is really exciting. Okay. Challenge number 2 was making that high efficiency. So now we can start it, we can get usable voltage out of it, but if you can only do that with 20% efficiency, you're losing 80% of that small amount of power you started with. So another 50 slides and several human years worth of work, and we were able to improve the efficiency of this process as well, so that now you can extract the energy not just at low voltage, but also at high efficiency from that low voltage. Okay. The demo ends up looking pretty similar. So you have a thermoelectric generator, and it still starts up automatically. We get a good regulated voltage at the output. And then now if you take the thermoelectric generator away and it starts to cool down, eventually the whole circuit dies. Okay. All right, challenge number 3 then is using that for something. And in this case, we're looking at sort of wearable medical devices. So same challenge, okay? But now we have the additional challenge that you have with most bioelectrical measurements, which is that people move. People like to move. And every time you do that, it messes with the signal. So we like to think of heart ECGs, for example, which is a good bioelectrical signal to measure because people have one and it's readily accessible at the skin surface. And we always imagine sort of this perfect waveform, right, that we all recognize. And in reality, it's not. The baseline sort of wanders around, and there are other artifacts that we need to deal with. And especially if you're building something wireless and batteryless, you assume people are going to be moving around. So one of the challenges is sort of this wandering baseline, where if you just use a reference, then every time you cross over that reference, you say, I have a heartbeat. But now if that reference is just fixed, you start and the signal wanders down, you don't see it, right? So you miss a heartbeat. So this again is sort of the naive approach of just using a threshold and where it fails in a pretty simple case. So one thing we added here is the ability to track this, right? So you can move your threshold as your signal baseline moves. And now, it's a simple algorithm, but now you don't miss those heartbeats. There are other artifacts. So there are sort of fast artifacts where sort of there's this quick movement in the baseline, but then it moves back, right? Which again, even with an adaptive threshold, you're going to think now you're going to have an extra heartbeat or maybe 2 extra heartbeats. So the approach we took here is that now if you look not just at the original signal, but if you look at the first derivative of that signal, heartbeats always go up and down in the first derivative, okay? Whereas these bigger excursions, until they come back, don't go the other way, right? So here, we can sort of still have this threshold that moves around, but by looking at the derivative of this signal, we have more information to say, okay, well, if it doesn't go up and down in sort of the right window of time, it's probably not a heartbeat and it's something else. Okay. So other circuits that do that, right? And all of these have to operate now at sort of microwatt level powers. So this is what we call system on a chip, where we bring all these things together. So energy harvester, the circuits to do that heartbeat detection with the both of those artifact detection and logic, and a little wireless transmitter. So we built a little prototype of this, and basically so it's got 2 electrodes to measure ECG, and as soon as the thermoelectric is on the skin surface, this thing wakes up, starts measuring, and starts transmitting wirelessly the heartbeat. Okay, no batteries, no power source other than body heat itself. So these are just sort of demonstrations that this is working as it starts up, and now as it tracks, we can see both the higher and lower thresholds, and we're tracking the derivative now of that heartbeat signal. And then we did some simple experiments of motion artifacts, right? So measuring this seated, measuring this walking, stretching, running, and then looking at accuracy. Accuracy stays at close to 100% with sort of those motion artifact mitigation techniques enabled, and otherwise falls off pretty quickly for things like running. So this was sort of our first demonstration of just a body heat powered wireless sensor device. Okay, so just to go back and think, what is the connection here? So all of these are taking sort of this emergence of low power, low cost electronic sensors and bringing them into new application areas, trying to bring additional intelligence right to the sensor node to limit how much data you're transmitting, and then moving towards power autonomy and looking at other sort of packaging things like stretchable and flexible electronics. So these are applications we looked at because there's ones we were interested in, or because we got in touch with people who said, hey, is this interesting? And we like to say, yes, that's interesting. So we are interested in lots of things, especially things that get us out to the coast more often. So ocean environmental sensing, smart and precision agriculture, also, of course, being in Oregon State. And my own background in point of care medical diagnostics are still things we look at. And then sort of the broader applications of soft robots and wearable devices. So if you have applications that require custom sensors, or small, low power sensors, or other signal processing ideas, connect, let's chat. We're always looking for new ideas and new people to work with. So with that, I'd like to thank all of our sponsors. And as always, there's a white space. So if you know anybody, let us know. Okay, thank you.
Perfect. Thank you so very much. Okay, I know we have questions. Anybody in the room? Anybody online? Okay, well, I have questions, but I don't want to dominate. I was just thinking about that, and I'm looking at Francis a little bit around the wireless, batteryless operation of devices in seawater. And just wondering if you had thought about that step yet.
Yes. Well, it depends on, there's sort of a few questions I think embedded in that. So thermoelectric energy harvesting is something we've looked at, and actually we had an undergrad honors college thesis project around. Same basic idea, but now harvesting energy from the temperature gradient between the ocean water and the air just above it. So it's a small differential, but so is the differential between skin and ambient air. So we've looked at energy harvesting from that gradient as well. Whether it's better than solar just depends on whether you need it at night, because solar is a lot more abundant in that case. In terms of wireless, we are looking at other sensor systems. So wireless doesn't work underwater, and this, of course, is a known problem in things like there is no GPS underwater, so localization, stuff like that. So in those cases, we still imagine basically wireless at the surface talking to whatever sensors are down below.
All right. I'm seeing that Sana says there's nothing coming in online. Matt, I'm wondering if you can take our slides back to your contact information.
Yes.
So if somebody's being shy online, but they want to follow up with you, they can get back to that. For everybody in the room, I think this was a nice stretch of the biological conversations that we typically have. And I think that we are excited to think about the next steps. I have questions about lock boxes and sensors and seismic shaking and whether we can open a lockbox with a seismic sensor. So
Yes, definitely.
I like that answer.
It'll just take a long time and a lot of money.
How about no money? And we've got some time.
Well, then we have to have a longer conversation.
Fair enough. All right, everybody. For everybody. Oh, we do have a question.
We do have a question online. This is from Bob Cowan. Does the material need to be encased to function? He's speaking of the GALN.
Yeah, so the gallium alloys we use, they don't need to be encased, but that is how we form them into wires. So we can stencil them or print them, and then by casting more silicone around them, it sort of self-defines that sort of tube now that it stays in. So it's not required, but that's how we get it to sort of be stretchable and robust in the world. But if you just print it and stretch it, it still works.
Nice. Anything else, Sana, before I step all over? Okay, wonderful. For those online, thank you so much for being here. We really appreciate you being a part of these hybrid events. For folks online, my guess is there's not cookies left, but maybe there's a little coffee outside. So feel free to go on out and socialize a little bit. And thank you so much for being here, everyone. And thank you again, Matt, to our speaker.